Welcome, everyone! Today, we are diving into the wettest lecture of the semester. Take a look at the screen. This 3D molecule wearing a crown isn't just a mascot, it's the king of life. We're talking about H2O. Honestly, if it weren't for this specific bent little molecule, you wouldn't be sitting here today. You'd be a literal pile of dust. So let's explore the molecular matrix that keeps us all afloat. Before we get our feet wet, let's look at our roadmap for today. I've laid it out as these droplets on the leaf here. We'll start with geometry and the magnetism of life. Move into the famous hydrogen handshake. See how water acts as a plant elevator. And finally, we'll solve the mystery of why ice doesn't sink your local ecosystem. It's a packed journey. So, let's get moving. Now, to understand water, we have to understand the power struggle happening inside it. Look at these values on the left. Oxygen sits at a 3.44 while hydrogen is trailing at 2.20. In the world of chemistry, electronegativity isn't just a number, it's an electron hogging contest. Oxygen is the ultimate bully here, pulling those shared electrons toward itself and creating a very tense relationship. Because oxygen is such a hog, we get what we call a polar covalent bond. Notice those little Greek symbols on the diagram, the delta plus over the hydrogens and the delta minus over the oxygen. This doesn't mean it's an ion. It just means there's an unequal sharing of wealth. Think of it as a very lopsided partnership where one side is always just a little bit more negative than the other. Now, why is water bent? Why isn't it just a straight line? If you look at this 3D model, notice those two big electron clouds on top of the oxygen. Those are lone pairs, and they are the ultimate personal space invaders. They push those hydrogen atoms down with such force that they're locked into that specific 104.5 degree angle you see highlighted in bright yellow. This shape changes everything. When you combine that bent shape with those polar bonds, you get what's on the screen now, a permanent dipole. If you look at this heat map, the red area around the oxygen is electron-rich, while the blue around the hydrogens is electron-poor. That big arrow pointing upward, that's the net vector. It means water is essentially a tiny molecular magnet, and that magnetism is where the magic happens. This magnetism leads us to the hydrogen bond. Now, look closely at this diagram. You see the solid black lines? Those are the real covalent bonds inside the molecule. But look at that dotted blue line. That's the H bond. It's an attraction between the delta plus hydrogen of one molecule and the delta minus oxygen of its neighbor. I like to call it molecular flirting. It's not a permanent marriage, but it's a very strong attraction. But here's the thing. Geometry matters for these flirts. If you compare the two sides of the screen, you'll see a green check and a red X. H-bonds are at their strongest when the three atoms involved form a perfectly straight collinear line. When they're bent, as you see on the right, the bond is weak. In nature, structural integrity depends on getting these angles just right. Water is also a massive social butterfly. If you focus on the central molecule in this cluster, you'll see it's connected to exactly 4 neighbors, because it has 2 hydrogens to donate and 2 lone pairs to accept. Every single water molecule can form 4 hydrogen bonds. This creates a beautiful symmetrical tetrahedral arrangement that gives water its unique structural strength. But don't let those static diagrams fool you. In liquid water, it's total chaos. Look at this 3-panel sequence. Those dotted lines are breaking and reforming every few picoseconds. It's a high-speed game of musical chairs where nobody ever sits down for long. This flickering cluster is why water flows so easily while still staying connected. This connectedness leads to 2 big concepts: cohesion and adhesion. Look at this droplet hanging off the leaf. Cohesion is water sticking to itself. That's what keeps the drop together. Adhesion is water sticking to the leaf surface. Have you ever wondered how water can just hang there without falling? It's these two forces working in a tug of war against gravity. Let's put that into perspective with a giant sequoia. How does water get 300 feet up without a pump? Look at the magnified xylem tube on the right. Because of H-bonds, the water molecules form a continuous chain. When one molecule evaporates at the top, it pulls the next one up and the next one all the way down to the roots. It's a 300-foot tall molecular elevator. Water also protects us from temperature swings. Look at this energy tax infographic. Before water molecules can move faster, which is what heating up actually is, the energy has to first go toward breaking those H-bonds. See the flame icon targeting the dots? That energy is spent on bonds before the temperature gauge even moves. It's a built-in safety buffer for the planet. This applies to you too! Your cells are busy making ATP, which generates a ton of heat. If you were filled with almost any other liquid, you'd boil every time you went for a light jog. But look at the thermometer in our cell icon here. It stays stable. Water absorbs that metabolic burn, keeping your internal chemistry from spiraling out of control. And when we do get too hot, we sweat. Look at the molecules on the skin surface. The ones colored in red are the high-energy, hot molecules. When they evaporate, they take that heat energy away with them, leaving the cooler blue molecules behind. It's not just a mess on your gym clothes. It's thermodynamics in action, cooling you down one molecule at a time. Now, let's talk about the density paradox. Usually, solids are denser than liquids in sync. But look at this iceberg. It's a massive block of solid water, yet it's floating on the surface. This single anomaly is the only reason life in our oceans and lakes survives the winter. If ice sank, our water bodies would freeze from the bottom up, turning every lake into a solid block of ice. So, why does it float? Compare these two boxes. Box A on the left is liquid water. It's chaotic and tightly packed. But look at box B. When water freezes, the H-bonds lock into a rigid hexagonal lattice. This actually forces the molecules further apart, creating those empty voids you see in the middle. More volume with the same mass means lower density. Ice is literally full of holes. This creates a thermal blanket for the world. Look at this pond cross-section. The ice sits on top, insulating the water below from the freezing air. Down at the bottom, the water stays at a relatively cozy 4 degrees Celsius, the sweet spot for liquid density. While the surface is a frozen wasteland, the fish underneath are doing just fine. Moving on to water's role as the universal solvent. Chemistry happens in water because it is excellent at tearing things apart. Look at how the water molecules in this diagram are swarming that salt crystal. They don't just sit there. They use their partial charges to wedge ions out of the lattice and pull them into the liquid. It's a molecular scale demolition crew. When they pull those ions out, they form what we call a hydration shell. Notice the orientation difference in these two diagrams. For the positive sodium ion on the left, the red oxygen heads face inward. For the negative chloride on the right, the white hydrogen tails face inward. It's a perfectly organized molecular cage match that keeps the ions dissolved. And it's not just simple salts. Look at this complex protein ribbon. Water coats these giant molecules in a shell of hydration, interacting with their polar surfaces. This shell is what keeps protein suspended and functional in your cytoplasm. Without this water coat, your proteins would just clump together like old flour and stop working entirely. This brings us to the big picture, the aqueous matrix. Look at how busy the cellular environment is. It's filled with ions, nutrients, and enzymes. Without water providing this fluid playground, these molecules would just be static junk. Water isn't just a container for life. It is the medium that allows the entire dance of life to take place. To wrap things up, remember, stay hydrated or dehydrated. We've seen today how a simple 104.5-degree angle determines the height of trees, the climate of our planet, and your very survival. Water is the most extraordinary substance in the universe. Don't take it for granted, otherwise, things might get a little too salty for comfort. Thank you.